All right, so I have put a tentative, and I say tentative grading for the score. B, C, and A. D obviously to the left. D is scoring less than random, or F. But most people scored well. And when you see the score this week, remember to put the grade on it up above. There will be no grade on the exam. We haven't really decided on the final grades, but this is approximately how they will be split. Any questions on that? All right. Let's let that stay for a while. The exam was perfectly reasonable. It was a little bit tough. No numerical questions to ask. For example, the question, will you have bigger or smaller parallax as you observe from Mars? Bigger or smaller? What does parallax mean? It's a bigger parallax because the baseline is longer. Parallax, remember, was the angular distance that you could see a star when it is spring versus fall. Yes?
How are we supposed to know if Mars was further or closer?
To the sun?
Well, you said it was a different star, wasn't it?
No. You know, I'm sorry, I have to assume that you know that the planets go in the order that they taught my son in kindergarten. First comes Mercury, then comes Venus, Earth, Mars, Jupiter, blah, 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 blah. He learned that in kindergarten, so I figure you would know that Mars is further out from the sun than the Earth.
But you don't know if it's further from the star.
It doesn't matter if it's further from the star. Besides, they're all the same distance from the star. Come on. You form the parallax by having one eye on Mars when it is March, another eye on Mars when it is April, and you see an angle. If you put these two beacons together, the angle is smaller. That's parallax. That's how astronomers measure distances to reasonably nearby objects. Measuring how much a star moves relative to other stars. All right, so, all right, anyhow, that's how we did. All right, now we're moving on to some very conceptually difficult object problems. This will be, from here on, the course is going to have a lot of difficult material. The first, it was already a little bit complicated to understand what Einstein meant by special relativity. Today we're going to talk about what he means by general relativity. Here is an example. This is an image taken with the Very Large Telescope. With the Hubble Space Telescope. In the yellow are, well, whatever the color this is. Yellow. What color is that? Orange. All right. These orange guys are galaxies, big galaxies close by to us, roughly close by. They're about half the distance as the blue galaxies seen in the background. Now, believe it or not, this and this are the same object. And so is this, and I think this. There are several copies of this one object. What the hell is this? This is known as a gravitational lens. Einstein spoke about gravitational lenses, but he had no idea what the future would bring him. And we'll talk about what a gravitational lens is and why it's important. Yes?
What are the orange dots again?
The orange dots are nearby galaxies that are elliptical type galaxies. And the background dots are young galaxies just forming, and they have a lot of material in them. They're forming blue stars as they just turn on. This is a magnificent photograph, and I'll show you some more later. Okay, let's let's go over Einstein's career. He was quite busy in the years after 1905. In 1905, he published 3 really important physics papers. And he was don't write this down, it's all in the notes. Jeez, you guys, why are you writing this down? Because everything's in the notes. The special relativity was only one of the 3 objects he published that year. It was quite the year, a golden year for him. The photo effect he talked about earlier, and thermodynamic fluctuations in stat mech he did as well. These were very important for physics development. And the photo effect, in fact, he won a Nobel Prize for. The discovery of the photo effect, because he said, look, photons come in, hit a metal, and then the electrons jump off the metal, and that is because the photons come in as discrete objects, and the energy is all concentrated at one point, and therefore photons exist. This was in 1905 when evidence for this was very weak, and he showed that they had to exist. And he won a Nobel Prize for that. He didn't win a Nobel Prize for his relativity theory, which was the most amazing theory of all, namely because the Nobel Committee probably could not understand it. And it's serious. They said about special relativity, they threw up their hands and said, people said, Jesus, maybe 10 people can understand this in the whole world, not us. It was conceptually unbelievable. All right, so he worked on mathematical physics, had lots of important results at that time. All right, but while he was working until 1907, 1915, he finally released his general theory of relativity. In the meantime, in 1907, he realizes, oh, I can understand how this works by using the equivalence principle. He realized that his perturbation theory can be extended to gravitational fields. Now remember that we talked about relativity in the absence of any gravity. An object was moving, another object caught up to it. None of that was done in the presence of a gravitational field. He left that out because he couldn't handle it. It was too complicated. And so the whole theory was special, meaning he just outlined the frames of reference, and general, meaning a theory that works in the generalized case of a gravitational field. And that took him 10 more years of work to realize how to do it. All right, so in 1912, he accepted a professorship at ETH in Zurich, Switzerland, where he had been an undergraduate. And he worked with Marcel Grossmann, and he thought he needed this mathematics called differential geometry, mathematics that's so far above calculus you wouldn't believe it. How far, has anybody gone beyond calculus in this course? Okay, what have you taken? Okay, differential equations. That's certainly next stage, and it's really important. But to learn differential geometry, you need to take about 2 or 3 more years of math, and finally they'll give it to you when you're a senior at Cal. All right, so don't be afraid if you don't really understand this. I'm not going to try to explain how differential geometry works. Okay. In 1915 was the year he published it. He realized that gravity is a distortion in space-time. What do we mean again by space-time? Space-time is 4 dimensions, x, y, z, and t. And you cannot break t off and say that the time is invariant or it all flows by itself. No, it does not flow by itself. X, Y, Z, and T. The time is integrally part of the equations. How does this work now? Okay, here gravity. His general theory of relativity was primarily, as I said, a theory of gravity. Now, the question was, as we talked about Newton's work, he could not understand how gravity could be this quote-unquote force that produces action at a distance. How can a planet produce a force field that pulls a satellite to it? What is it doing? Is it sending out little ropes that tie to the planet, to the little force field, and pull it in? What is it exactly doing? How does this work? And Newton could never understand how it worked, and he just gave up and said, oh boy, I don't know what it is, and he knows that the force field fell off as 1 over r squared. That was important. But Einstein, and this was amazing, Einstein realized that the distortion, the gravitational field of the planet sets up distortion in space-time. And distortion in space-time is what bends the orbit of the object that's traveling. And that is how it works. Now, it's very, very complicated to understand this. Now, as I said, space-time, four-dimensional. There's a four-dimensional space and time. And here's the idea. Space-time itself can be curved. Now, this is very hard to visualize. And we usually visualize it by a sheet of rubber, a rubber sheet on which you put a heavy ball. And that makes the sheet bend. But remember, that is a two-dimensional sheet, 2 dimensions describe the sheet, and it's bent, but then it's flat in 3 dimensions. Now, the reality is, you imagine you take a sheet in 3 dimensions and stretch it in 4-dimensional space-time, and it bends in the same way, but the curvature is in the 3-dimensional space, not the 2-dimensional space. So when you see these bent sheets, remember they're not the right dimensionality. You're not going in a straight line. You're not traveling in a curved space of 2 dimensions. It's different. Okay, so now let's talk, before we get to that, let's talk about the equivalence principle. And this is Einstein's realization that he did in 1907 or so. Suppose you are sitting in a box, and there's a tree outside of you. It's a pleasant day. The box is completely enclosed. You can't hear anything from outside. What do you feel in a box? Well, you feel a force down this way, the gravitational force. What is the difference of being in a box that's constantly accelerating? It's in a rocket ship that's accelerating at 9.8 meters per second squared. That's the acceleration of gravity. You're going up. Now, what is the difference? You measure yourself on a scale, same weight. You drop a ball, it falls. Everything's the same. In fact, Einstein said the frames of reference are equivalent. There is no difference between these 2 frames. None. That is, equivalence means that the laws of physics, all the physical experiments you can do, will give you the same result. Yes?
Is an example of an inertial reference frame?
Neither frame is inertial. Inertial reference frame is when you fire your rocket and then you turn it off, and then you coast with the rocket, and everybody's weightless. An inertial reference frame is a weightless frame. This is very much a frame in a gravitational field like we are now. Okay? Is that clear? All right. Now, what does he mean? There's nothing, what he's saying is there is nothing you can do apart from hearing the noise and vibration. That doesn't count. You can't look out the windows. You're not allowed to see anything. And there's no physics experiment that you can do that will tell the difference. That's pretty amazing. But that's what he said. All right, we're going to say that's right. And supposing let's just say that he's right. All right, now, here's an example. If you're in a rocket ship that's being pulled up by, it's a boosting rocket ship boosting up that way. Now, what happens if you shine a light across the frame? If you shine a light across it, the light, here, let's All right. All right, he shines a light. And when the light is received on the opposite end, now let us say the ship is you're just moving, like in a railroad car that's just moving. It's not accelerating now. Let's not that example. You fire the ship up here. Now, the frame, by the time the frame is over here, let's say it's going to bounce right off here, off this wall. Here's the photon, and it was aimed here, and the photon really travels up this way, the way the man travels up this way. It's traveling in straight lines. You know, you shoot it, it's up at an angle, because you look at it from the ground, and oh yeah, it sees, yeah, the laser beam shot, and now it's at an angle, and it goes back, like this. But now, put it in a rocket ship. If you have a rocket ship here that's accelerating you, you fire your rocket, and then the ship is not where you think it would be if it were coasting. It's firing in a rocket. What that means is that the laser beam is not going to hit on a straight line. It's going to hit down. It's going to be tilted downward, because in the meantime, this thing has moved up. It's moved up, and the beam goes like this. It bends a little bit. All right? So it bends in the gravitational field because you fired the beam, the rocket ship pushed you up, the beam knew nothing about the rocket ship, and it just bends. So he said, okay, this bends. But now he says, well, what about the equivalence principle? The equivalence principle said there was no physics experiment you could do that would tell the difference. So you know that the beam is going to bend. There's no question. And what that means is Einstein said, okay, if this beam bends, so will this one. The gravitational field has to be equivalent to the rocket ship being accelerated upward, meaning that the Earth's gravitational field bends a light beam. A light beam does not go straight in a gravitational field. That's what it means. Light bends in an accelerated elevator. It must bend in any gravitational field. Any gravitational field. That is the first consequence of his theory. The equivalence of the frames of reference means that they have to behave the same way. All right, that is incredible power from one simple statement, that this law is absolutely equivalent. All right, so this is why, and I'll show you later, why we see gravitational lenses in space. Okay, let's try something else. Let us try time dilation. Here's Jackie, and here's you. All right, now, they're going to communicate. The ship is accelerating upward like this with a rocket on it, pushing it up. And you compare that to the situation on the Earth. Jackie sends off a beam to the person up on top. What does he see? All right. Now, you synchronize your watch with Jackie. You go down and compare watches, and they're beating at a certain rate. Now, the watches, meanwhile, the ship accelerates then, and the watches flash. Bang, bang, bang. What do you see for the watch flashing? You are going up away from that flashing light that she sends to you. She sends to you a beam which you see it receding from you, or at least it's not moving as fast. And the Doppler shift means it's going to be a little bit longer between intervals. Just a little bit longer. Yes?
Then the speed of light is always the same, and then
Yes?
and then your frame is kind of moving upwards, so the light is being slower.
That's right. That's right. And every time you move, the object is slowly, slowly, slowly catching up to you. All right, so, all right, moving away from Jackie, you see a time interval between her flashes. She shoots, and you're rushing away, and you see a time interval. So it's not quite the same as you would have thought. All right, so that is to say, you see a longer time interval between her ticks. And that means her clocks are running slower than yours. They do not run at the same rate. What does that mean? Now, Jackie, on the other hand, she sees you firing the beam every second, but she then accelerates to it up there. She accelerates to it, and that means she sees the photons come to her with a redshift of everything, and that means they're coming faster than she thought. And the time interval between the ticks is shorter. So Jackie sees a shorter time interval between your flashes and hers. All right, so that is to say, she judges your time moves faster up here than down here. And everybody agrees the situation. This is not like special relativity where you disagree as to what's happening. You absolutely agree. What does that mean? All right, in the equivalent, now you take the frame of reference here in the gravitational field. There's gravity here and gravity here. This is equivalent frame of reference. Time moves more slowly where gravity is stronger. Where is time moving more slowly? Sorry? Where is that? They both feel the same gravity. Which is stronger? No, come on. You've got it. You're almost there. Why? Earth, that's it. One place, because it goes as 1 over r squared. R squared is like 5,000, 6,000 kilometers to the center of the Earth. Well, it's r has changed by 10 meters. It's, 1/100th of a kilometer is just a little bit, but r is a little larger here. That means the gravitational field is a little weaker. That's why. So, yeah, it's weaker up there. And because it's weaker up there, the time moves slowly at the bottom compared to the top. Now, isn't that weird? Now, that means that if you set your clocks and you compare the clock rate, you set it down in the basement of LeConte Hall, and you go up to the 3rd floor, the clock rate's faster up there than here. Do you know that that has been experimentally verified, exactly that experiment, by sending a beam up from the bottom of a well up to the top floor, and yeah, it's exactly right. Do you know where this is used? Who has to make use of this? Anybody have GPS on their clocks? GPS receivers? You do, don't you? Do you know that the GPS receivers have to take into account this effect? Because if they didn't, everything would be screwed up. They have to. Their time accuracy is so precise. They've got to measure the relative. They've got to include the relativistic effects, and it makes a real difference. So everybody took physics, whatever, physics 10 or something, or astronomy 10A. All right? It is essential that be the case. Now, here's another thing that Einstein's theory says. He says that if you follow the orbit of Mercury, this is drawn very exaggerated, the orbit of Mercury is roughly an ellipse. This is drawn very oblique, very large ellipse. It's roughly an ellipse. Now the question is, an ellipse is a closed circle. You know, that means you go back and back and back on exactly the same elliptical shape time after time. And in Newtonian mechanics, that's absolutely right. If Newtonian mechanics of a point, sun, and the planet were the whole story. But the Newtonian mechanics properly has to take into account the mass of Jupiter, the mass of the Earth, of Venus, all these other perturbers in the solar system, all of which give a little bit of perturbation. Now, what do we mean by perturbation? Here's this angle is 1 point, and this is another ellipse. And you can characterize that by the precession of the perihelion. Perihelion is the point of closest approach. Here the perihelion is this way. Here the perihelion is this way. That's a big precession. Okay, now, Newton's law, should the precession of the perihelion, due to the gravitational influence of the planets, it does precess. It's more complicated than we've talked about, but it's a very small effect. And this precession was measured in 1800s. But it never agreed with what the observations said. Newtonian law could not account for the exact precession of the perihelion of Mercury. There was something slightly wrong, and they didn't understand it. They even made up a name. They started looking for another planet that might be perturbing the orbit of Venus a little bit. They called it Vulcan or something like that, meaning a planet, a fiery planet close into the sun. And they said, well, maybe Vulcan is just in there real close and we can't see it. Well, there is no such thing as Vulcan. Okay, discrepancy was known to exist, and people didn't know what to do with it. But Einstein knew of it and used his general relativity theory, and he explained it perfectly. It assumed that time and space were absolute and flat, and it turns out that when Mercury comes into the closest point of the sun, the clocks move a little more slowly, and space is more curved, and there's another term that gets added to the forces that are pulling the sun and the earth together, and slight deviation is seen from the 1/r² force of Newtonian physics. Very, very slight. Newton would never have seen this, as much to require much better data than he knew about. You know, they couldn't take data at that accuracy. All right. So, all right, the predictions of general relativity match these observations that nobody really thought about anymore. It matched them precisely. And here Einstein had made an imaginable, incredible theory about space and time. He was not thinking of Mercury at all. Not at all. And then he said, well, what can I apply this to? And he looked around and saw a few things he could apply it to. So we'll talk about those. Okay. Now, here is, there's the sun, and here is Mercury going around and around and around. All right. Now, it didn't, all right. So, Mercury did not obey a closed orbit. Okay. Precession of the perihelion was real. All right, and Einstein, out of the blue, calculated it, and it matched the observations. And unbelievable, when it matches the observations, and it matches a very small effect, it amounts to a motion of 43 arc seconds per century. That's not a big deal. You never see that if you're looking at Mercury with a telescope or looking at it with ordinary something. You've got to have a real measurement of it very precisely, and you could see the effect. Very small deviation. But what happened? This is out of the blue comes this crazy, crazy theory, and it matches a prediction. Well, that is the sort of thing that makes scientists into believers. My God, how did you ever predict that? They can't believe what it did. and it worked and it explained a fact that nobody thought about for a long time. It just explained it cold. All right, so now what is happening? Here is how we're going to understand this. Again, we have a sheet, and the sheet has a ball in it, say a heavy ball, and it depresses the sheet. Now, this is the wrong way to think of it, but it really has to be, this is a two-dimensional world bent into a straight three-dimensional sheet. I mean, in 3 dimensions, the sheet is, you can draw how the sheet is bent. The reality, of course, is it's a 3-dimensional sheet that's bent in 4 dimensions. All right? Just think of it as that, and don't worry if you can't visualize it. It's okay. You don't have to. It's not necessary to visualize it to understand what's going on. All right, so light always travels at a constant velocity, but it travels on this curved surface, is what Einstein said. It travels on the curved surface of space-time. That's the way it goes. It follows the straightest path through this, and space is curved, so will be the trajectory of light. Again, this was in 1919. There was an eclipse, a very favorable eclipse, and astronomers went out to observe it. Now, what is it that they observed? So, to observe an eclipse, what they do is they note the sun is going to be right here. Going to be right here. This is going to be obscured by the moon. So we can see it's a little dark already. And then there are going to be stars in the field here, 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 here. Bright stars. Okay, now, this means that light has gone in a path. Now I'm going to draw it from the side. Here's the stars, and here's the sun, and here's us. The light has come and it bends a little right here. This is not a straight line. So that means that if you drew continuation of a straight line, it would look as though the star had moved out. It goes to this position, and the star moves out. Moves out. Moves out. So that is to say, 5 stars or 4 stars here, all of them are pushed away from the sun because actually the light has been bent as it neared the sun. That was Einstein's prediction, and astronomers went to see if they could measure this. And in South America, I've forgotten where, they're up on a mountaintop, and they famous people up there, and my God, well, it's not very good data. It's pretty crappy because their equipment, it's a problem to do anything. But they claim they saw the effect. They saw the effect. And instantly, Einstein became world famous when they realized this. All right. So this was the effect of what happened. Now, what is it that's going on? Let me show you a little bit. All right, now, this verified the Einstein theory, and it made him a celebrity. And let me show you again what it really means. For example, here is a picture, again, of a 2-dimensional sheet bent in 3 dimensions. Here's the sun, for example. And the sun, here's us, and here's the source. The sun bends the path of the light, and it looks as though the object has moved out here. because you measure the angle between these stars, and it's definitely wider. Well, it's wider. All right? So each path is the shortest distance from the observer, but the paths do not appear to travel on a straight line. Yes?
So I see that there's one source, that one point at the end of the sheet. So that means that one star would look like two stars?
That is for an extreme black hole and extreme bent curvature, and that is a situation we saw on the picture I showed at the beginning of the lecture. Now, with the sun, you don't have any such object that makes it. You can't really find stars that are perfect. Instead, you find a star that's just bent a little. Okay, so that's all. That's the best you can do. Okay, and it's bent about 1.5 arc seconds on the sky. This requires careful work. But that was a crazy prediction, and yet it is confirmed by observations. Now, that is about as, this is really something, and this alone was enough to make Einstein was incredibly famous. All right, gravitational lensing has been seen all over the place. For example, here is an object it has very dense mass around it, and it curves the object far enough that a real object has light coming this way or light coming this way, and we see it either side of the object. We see this, we draw a line to it, and we see it here and here. This can be seen, and we can, it's really kind of amazing. All right, now, typically what you have to look at is very long path lengths. And that means you're looking at very distant objects, very high redshift galaxies, or something called quasars, bent by intervening matter in space. You don't, within the solar system, there's no situations that allow us to see this. So Einstein would not have known about those because galaxies and the whole shebang wasn't known or studied until the 50s. And he died in early 50. Or 54, I think. All right. Here's an example. This is one of the first. This is the first lenses that were seen as multiple objects. This is a picture of a galaxy, but there are 4 objects on it. 1, 2, 3, 4. This is part of the galaxy itself. These are the same object, seen 4 times in the symmetry of the object. This is 1, 2, 3, 4 is drawn in another dimension, but this is an object of 4 objects of 1 quasar. In order to make this work, it happens to be that a galaxy is out in space, it's bending the light, and right behind it, very far behind it, but exactly on the path, there's a quasar which puts out light that gets bent. So this is this is what happens if you have an object there. Or take a look at this object. This one's crazy. Here is an object, here is a galaxy. And what here? All this is a gravitational ring. Because the object is symmetric, and there's an object is here, an object is here, but an object can be anywhere around this plane and still give a bent image. This is a gravitational lens, a gravitational ring of a galaxy directly behind another galaxy. So you make it in 3 dimensions. And that's pretty crazy. Okay, how about this is one of the most famous ones. What in the world is this? Yeah. Well, this is a massive cluster of galaxies. We'll talk about that later in the course. This cluster is a huge agglomeration of mass. Each of these things is a galaxy. This is a galaxy as big as our Milky Way, or bigger. Here are hundreds of objects brought together, just piled into a big mass. Why in the world does that happen? What in the world makes this? Well, wait until, this is not going to be touched on until the end of the course, but we will talk about it. For now, we'll just say that this is a massive, glump, and here these arcs are gravitational lenses of background galaxies that have bent light. Now, Einstein would have flipped out had he been alive to see any of this. Of course, this came 20 years after he died, or 30 years after he died. Okay? But this is an example of lensing. Questions? Does that make any sense to you? You've taken lots of math. In the back? You think it makes sense?
How come the images aren't always circular? Like the one that you had before, there's only 4.
That has to do with the fact that the mass distribution that's bending it isn't exactly circular either. It's not a star. Stars are circular, but a galaxy has a mass distribution of an elliptical data set, and it doesn't produce a nice round image. Okay, it's just not, so that's it. It's just not circular mass distribution that's bending it. More complicated. This is more complicated as well, especially these arcs. This and this, but these are magnificent. They're telling us that the mass distribution is somewhere in here, and it's got a lot of power to bend the objects. Incredible power. This is a problem. This actually is evidence for dark matter, and we'll talk about that at the end of the course. Dark matter is stuff you can't see, and here's evidence for it. Okay. Here's another. This is the one at the beginning of the course. The blue objects are behind the red objects. This is the same object here and here, and they have been gravitationally bent. Multiple image, just magnificent object. Or another object, gravitational lensing of this foreground cluster of galaxies. This is from the Hubble Space Telescope, I think. Or another one, gravitational arc of this mass. Or gravitational arc of this mass. Everywhere you look in the faint universe, you can find evidence of gravitational lensing. It's totally unbelievable how much is out there. And this is confirmation of Einstein's theory right in front of you. Right in front of you. Here's another perfect ring. A quasar is right behind a galaxy, and it gets lensed into a ring. So, you can look at this and you would say, oh, well, this is nice and round. That means there is no anisotropy, it's called. That is to say, that is the gravitational field must be circular in that case. And so that's a demonstration of the circularity of a particular field. The other objects were not circular, but that's okay. All right, so Einstein got rightly famous at that. Arthur Eddington was the astronomer who led the way in 1919, a very famous astronomer of his own. We'll see that later, what his fame. All right. Okay. And here, this is a British newspaper, The Times. Banner headline, Revolution in Science, New Theory of the Universe, Newtonian Ideas Overthrown. That's a pretty good headline to have for you one day. Nobel laureate, Max Born. General relativity is the greatest feat of human thinking about nature. Paul Dirac. By the way, Max Born was a very instrumental physicist in the birth of the first quantum mechanics theory. He's a very, very well-known guy. Paul Dirac was the very best physicist of the 30s. He's from Cambridge. I think from Cambridge. and totally magnificent. Here's what he says. Probably the greatest scientific discovery ever made. International media was, of course, very much onto him. He's a real hero. And these two laws, these two papers, 1905, 1915, were really all he had to do. He did lots of other stuff in his life, but those two papers were so famous. They're in German. If you read German, you can look at them. But they were stunning. Now, here's the idea. You put a sheet, and the sheet has little coins on it, weights, 10 pounds, 20 pounds, 5 pounds. You know the 5-pound weight doesn't deflect it as much as the 10-pound or 20-pound weight. So the effect of this 5-pound weight is not as significant as a 20-pound weight. And this gives you action at a distance. The sheet is bent. You move around here, and because it's bent so much, you move. You move in proportion to the bending of the sheet and the weight of the coin. So Newton would have loved this. Of course, he wouldn't have understood the math. Because Newton had just made up the math to do his needs, there was hundreds of years of math ahead of him that had to be worked out. And, of course, he didn't know any of it. All right? Now, so the idea is matter distorts space-time like weights on a taut rubber sheet. Greater the mass, the greater distortion of space-time. That's what you have to remember. But remember, the curvature of space-time is not the same as this curvature of a two-dimensional surface into a three-dimensional geometry. It is instead a three-dimensional geometry that's curved into a flat four-dimensional space. So remember, you always have to add a dimension. All right. That's what it says here. Okay, this picture is not quite correct. Now, here's the rules of geometry that you learned very well in high school. You learned all about these rules. In a triangle, the sum of the angles is equal to 180 degrees. Lines that are parallel somewhere in space can be made to be parallel forever. The shortest distance between 2 points is a straight line, and the circumference is 2 pi times the radius. These are basic rules of geometry, except they're only special because this is drawn on a flat sheet. If instead you made the rules to be, this is a flat, so-called a flat Euclidean geometry, known by these rules, you could instead have a geometry defined on a surface of a balloon, for example. What are the rules for that? Well, the three angles here make up a triangle, but these angles sum to more than 180 degrees, every case. Two lines can be parallel if they're really on the surface, and they're straight lines. They can be parallel, and they'll still cross, like lines of longitude. How come lines of latitude don't cross? Lines of latitude the same? Are they straight? No. You know, you take an airplane, and you wonder why, if you're flying to Europe, the airplane goes so far north. It doesn't follow, you know, Europe is about the same latitude as we are, but it doesn't follow that line of constant latitude. It follows instead a straightest path it can. And how do you define a straight path? Put a pin on one point, a pin on the other, stretch a string between them, and that is the straightest path, the shortest path. Shortest path is straight. So in that case, the shortest paths of longitude, those are not short paths of different latitudes, but except for the equator, and it intersects everything. The shortest distance is a curve. The shortest, if you measure the circumference, it's less than 2 pi times the radius. So the rules of geometry are completely backwards. And if you then have a geometry that has the curved geometry, this is known as the saddle-shaped geometry. It, after all, looks like a saddle. In this case, the laws are reversed. Two lines that are parallel diverge at infinity. They don't cross, they diverge. Two lines, the circumference is greater than 2 pi times the radius. Shortest distance is a piece of a hyperbola. Sum of triangles is less than 180 degrees. Now you know how you can tell if this sheet, if you tried to flatten this out onto a sphere, you have to take a sheet of paper and flatten it into a sphere. You have to snip it at various places so it fits on that sheet of paper. In other words, you're expanding it, taking the excess, making the excess area, just smashing it down. But this one, if you try to fit this on a piece of paper, you smash it down, and you've got too much. You've got the material doesn't fit. It has to be folded over to make it fit on a sheet of paper. So this law has too much material out here. This one has too little material compared to the Euclidean space. Yes?
I thought you said that the shortest distance would be a straight line.
Well, this is drawn as a, this shows what it is on a two-dimensional surface that's embedded in a three-dimensional space-time. And so in three-dimensional space-time, you can see the lines aren't straight.
So, and also, what's the significance of some of the angles of a triangle being greater than 180 or less?
Well, these are signatures of the curvature. So if you're in a situation, you measure the sum of angles, and it's less than 180, it says, oh, we must live in a negative curved space. Okay? All right. So, all right, that is, and we, in Einstein's theory, can talk about 3 different types of geometry. This is the reason I brought that up, is that Einstein's theory makes it does not care what the geometry of space is. In fact, for the cosmological problem, it took us a long time to figure out whether we live in a flat, spherical, or saddle-shaped universe. Now, I'll tell you a little bit about how we did that, but we now believe that we live in a flat universe. And I'll tell you about that and all about it later in the end of the course. But Einstein's theory of relativity could work in any case. In this case, this is a finite universe, and the other 2 cases are infinite in extent. If you want a universe that has a finite edge, or just does not exist forever, then you want a spherical universe. And this is very hard to measure, but it can be done. Okay. Now, these geometries are not necessarily constant over the whole sphere. If you've got a star, it gives a little dimple of space-time curvature. A galaxy gives a dimple. But that's all right. That's okay. All right. Now, the free fall observer is an observer traveling along the straightest possible word line. That's what it means to be in free fall. The objects are all weightless. All right? And all those objects have an orbit that is determined by gravity. And that is what we mean by weightless and equivalence. Now, if you look at the orbit of a star, let us play a little bit here. All bodies of mass exert gravitational force according to Newton. You do not accept action at a distance. So what happens? If you have an elliptical orbit, our object goes in and out. Circular orbit, the object goes around and around in a ring, a constant ring. An unbound orbit, it gets bent, but it's not attracted to the object. All right. General relativity removed all the problems that Newton would have had. Mass caused curvature to bend, greater distortion of space-time, and freely falling objects bent that way. Now let me show you. Anybody see where the hell? Help. Oh, here I am. Where'd it go? Huh? I don't, yeah, I know, but I can't, I'm stuck. Huh? Where? Oh, okay. Thank you. Ah. There we go. Okay. Somehow it's all screwed up here. Here we are. Okay. All right, so here shows, here's a circular orbit. Now you note, this is a circular orbit about an object, and it's like a coin falling into a pivot, a deep object. Here's an elliptical orbit, and it's slow going out and then faster when it comes in, because after all it has fallen in the gravitational well. Faster, bang, and that's it. All right, so that's how it works. This is what Kepler's laws tell us. Kepler had no particular reason to understand what was going on, but Einstein provided a perfectly good explanation of the force. Okay, now here's the sun, and so you ask, well, what happens if the sun is if the sun's all condensed down? We'll take the sun and squeeze it down to a small object. What's it going to do, particularly to our orbit? Say we orbit, suppose this is us right here. Are we going to change? So let us move the sun down to a white dwarf. This orbit hasn't changed. What has changed is down here. You can get much closer to the sun. Very close to the sun. But the objects way out here, and orbits way out here, show no effect. Even if I make it into a black hole, where in fact there's no object shown, you could fall straight into the black hole. And you're stuck. You can't get out. But you could stay up here on the same orbit we have now, and nothing will care. That is how a black hole works. It empties. Everything gets dumped in here. Okay.
Wait, so no matter how much the object's radius changes, the orbits remain the same.
The orbits remain the same. There's no difference. Okay? If the black hole mass is the same. Yeah. Okay? All right. All right, so orbits are explained in a new way, and this is how the objects really should be thought of. We draw time up, space this way, space on the plane, and the object's orbit winds itself around time and time again as it goes around in a circular orbit. So this gives you some idea of the orbit in space-time. Okay. Rubber mat, the rubber mat is only useful for 2 dimensions, but when it goes to more dimensions, you have something else. All right, so the Earth, as it orbits around, follows this trajectory. This is a year from here to here, year, and it orbits around. So this allows you to think of the time as being equivalent to x, y, and z. So you draw it in 4 dimensions. Okay, so it returns to a different place in this space-time. The space-time is space and time as coordinates. All right, so the strength of gravity, here are the 3 cases I showed before. The sun, if this were the sun. Here's the sun if it's a small object, say a white dwarf, and the sun if it becomes a black hole. The only difference is the orbits near the center of the sun are bigger. They're more curvature is shown because you get closer to a black hole, more and more curvature. But other than that, on the outside, the orbits are the same. Okay. All right, so at a distance out here, the curvature will be identical to everything. Okay. Clocks don't run at the same speed as I tried to explain to you. The rocket ship and the analogy of a person sitting still in a gravitational field. This rocket ship is moving down here, it's moving a little slower than up here. Up here is moving faster than down here. What does that mean? All right, you're running away from Jackie, stretched out, redshifted. She perceives the object at a higher point to be blue shifted. All right, and the deep in a potential well, the clocks run slower. And this is something that has been experimentally determined to be exactly as given by Einstein's theory. Hard to believe this. Now let's look again, go back. Here's what we mean. What Einstein is saying is that if I have a clock here and a clock here, different points in space-time, this plot and that clock, they don't agree on the passage of time. This guy has a clock speeding faster than here. That's what he really means by this. The clocks slow down as you get into this black hole. If there's a black hole here, the clocks go slower and slower and slower and slower. If we were watching an object falling into a black hole, it looks like it takes forever for anything to happen. Well, of course, we can't do that experiment directly, but you can do the experiment on the surface of the Earth, and you can see that it works. So as you climb out of this well, your clocks run faster and faster and faster. In the well, they slow down. At the same time, the radial coordinate is stretched out, the clock slows down. This is exactly the same effect that we saw in special relativity. If you're moving faster, your space-time, the radius is shorter, the clock you're carrying runs slower. That's part of the problem. Okay. All right, gravitational redshift. That would mean that on the surface of a star, there is a redshift for every line that the star emits. Say it emits a line of calcium or hydrogen or anything, it then has to climb out of that potential well. And that takes energy from the photon, and that photon shows up as a redshifted photon. And that is observed. You can actually observe it on objects. You can see that they are slowed down as they climb out of the well. It's very amazing. Okay, this is what I said. Lower frequency means energy has been stolen from them as they climbed out. All right, so gravitational redshift has been observed again. This has been very well observed. All right, so space-time. Clock beats slower when you drop in potential, and that means that you cannot synchronize clocks. There is no way to synchronize all the clocks of people in a solar system. You can only synchronize clocks of people who are freely falling. If you're sitting at different points in a potential well of the sun, then your clock is slowed down according to the depth of the well. Now, these effects are very, very small. You'll never see them. It's going to be less than a second in 1,000 years. But they're there. The effects are very small. These are the three predictions Einstein made for his theory. Bending of light, precession of the perihelion of Mercury, gravitational redshifts. These are talked about in his 1915 paper, Ways to Check His Theory. He didn't know the results of any of them, but he was sure they're going to be okay. Because he had faith, his mathematics was accurate, was beautiful. The mathematics told him his theory had to be right. Now you can't understand that, and I'm sure it's ridiculous for me to say this mathematics is beautiful when it's differential geometry and so hideous you can't believe it. But there's beauty underneath it. You know, only a person carefully trained can see the beauty in a modern painting of nothing. I can't understand the beauty in those paintings, but somebody supposedly can. So okay, maybe it's the same difficulty. Anyhow, all right, now I want you to say, tell me what the answer is here. You know you're following the straightest path through space-time if you're standing still, you're moving directly from one place to another, you are weightless. Red, green, or blue. Red, green, or blue. Let me have a vote. Okay, red, green, or blue? I don't see, a lot of them I don't see. Red, green, blue. Okay. Are we going through, are we right now going the straightest path in space-time? No, we're not. Okay? If we were weightless, we would. That would mean that we're falling along a space-time path. Right now, we're resisting falling toward the center of the Earth. Blue is the answer. Okay? It's not because we're moving directly from one object to another. That is not what does it. It is because we're weightless. So those astronauts who are weightless when they fall, after the rocket takes them up, are traveling on straightest lines in space-time. Straightest paths in space-time. Photons are traveling on the straightest path of space-time. Okay. Okay. Now, there are other effects of Einstein's theory. One of which is very interesting, is known as gravitational waves. Gravitational waves will, it makes, let me see where, here we go. Suppose you have two black holes or two planets orbiting very close to each other, and they're spinning around, and they orbit like this. And the gravitational field, these are lines of gravitational field. The gravitational field and the curvature of that field can only travel at the speed of light. And so the objects are bending around and around, and they're giving different signals at different times saying where the field is maximum. And they send out a wave in that direction as they do it. This is similar to electromagnetic waves. If you have an electron orbiting a proton spinning around, it will emit a wave, except for quantum mechanics. But ignore that for the moment. All right, so this is an effect that you're looking for. All right. Now, this is the effect predicted. The line is the predicted observation, and the theory is the line is predicted from gravitational radiation of two very massive objects that are very tiny, two black holes that are two neutron stars that are orbiting very close to each other in a situation where the curvature of space-time is very real. And they've timed them very, very accurately, and they see a delay in the timing. What's shown is the year, and this is the cumulative deviation in seconds, okay? So since 1975, they've lost the orbit of these two stars around each other has lost 15 seconds of time that it should have had. And the loss is because of the emission of gravitational radiation. That's fine. It'd be nicer to see it better, to see it directly. We will talk about this more a little later. This is known as the Hulse-Taylor binary. The people who discovered this won Nobel Prize in about 1980. All right, and they saw a result that was consistent with gravitational energy, exactly as predicted in the theory of relativity. All right, so gravitational waves are thought of as like photons. Photons carry electromagnetic signal. They don't have any mass. They travel at the speed of light. Gravitational waves carry a gravitational signal. They have no mass, and they travel at the speed of light. And they carry a gravitational signal. That's the idea. And they were predicted to exist, and we've not seen them yet, but we're trying to find them. Let me show you an example. Okay, now, in order to detect this, you need a really massive laboratory to see this ripple. It's very, very small ripple. To do this, they've built an observatory called LIGO. This is the name of the observatory on the ground. And there's another one under design. LISA is being designed by the European community. And what do they look like? Here is LIGO. This is Eastern Washington. What it is laser beams are shot out here and back. This is a vacuum tube. They go out and back. This way goes out and back. And by timing the time it takes to go out one way and the other way, they can time the passage of space, and they're looking for vibrations caused by the gravitational wave. They've got one in Washington and the other in New Orleans, or not New Orleans, but Louisiana, in the swamps. Okay? And there's some others in Europe. That's an example. This is called LIGO. Here is a drawing. This is called LISA. This one has 3 satellites. And the satellites are on a crazy orbit that is very large orbit that is about 1/6 the distance between the Earth and the Sun. It's really a huge orbit, and it's orbiting just like this, and it goes around slowly. And what it does is it has laser beams going between the 3 stations, and they're detecting the coming of waves. They want to look for this wave to go by. And when the wave goes by, it'll make the distance between these objects will ring. It'll just make it ring a little bit. These are extremely difficult experiments. This will probably be launched within 10 years, I hope. And we'll possibly see this. What they're going to see will be anybody's guess. All right, now here's another fact. Here's something else you might look for. This is part of relativity. All right, suppose you want to go to Vega. Here's the Earth. And we know that the path to Vega is 25 light years along this interval. This is the path. But suppose we want to find a shortcut, a real shortcut, and we just look for the nearest wormhole. The nearest wormhole is a path that you jump in here, whoop, and you come out there in Vega. Now all you got to do is find a wormhole and jump into it. I don't know where they are. People. All right. But this is part of differential geometry. Maybe they're there. It's a shame if they're not there because wormholes are pretty neat for traveling. If you're going to travel and still obey Einstein's theory of relativity, you got to use wormholes. Now, how many of you saw that movie with the lady who talks? It's no, wait. It's a lady who they built a special piece of hardware. She travels. Contact. Has anybody seen Contact? Just one person? 2, 3? All right, this is assignment. All right, if you want extra credit from the exam, because you don't think you did it, you want to get more credit, tell me what Contact is like. Read Contact, see the movie. Get the movie somewhere. Anybody who wants extra credit for the exam or anything, you want to build some points in this exam, in this course, see Contact and then tell me what the hell's going on there. What they've done is this advanced civilization has built a pathway from here to here to here all over the galaxy, and it enables her to go to the center of the galaxy. She gets to the center of the galaxy and she has fantastic dreams, but she can't really tell anybody what happened. And everybody watches her and she looks like she's only been gone 10 seconds. If she was gone at all. Relativistic effects are, strange. And it's a pretty neat story. But it's based on this, not reality, but it's based on this thought. So if you want some extra credit, see that movie, turn it in a paper. It's worth at least a problem set. If you got tired of doing these problem sets, this will give you some points. All right. All right. All right, so we're looking for a wormhole. The problem is it might connect different points in the universe. This is unlikely, but there's nothing ruled out in Einstein's theory that says they can't exist. They could touch momentarily. Who knows? The problem is wormholes that people have thought about wormholes, and when they exist, they thought, well, you know, they're probably really narrow. If you jump in, nothing that says how big this is. You won't fit. One atom at a time will fit, but you probably won't fit as an object, as anything. So that's too bad. Star Trek has wormholes, doesn't it? Don't they travel in a wormhole? Yeah. See, these wormholes are well known. So just ask them how they did it, and that's the way you'll do it. All right. This is kind of interesting thing to do, but who knows? All right. What was that? Oh no! You drop your laptop? Oh gosh. Well, you hope that it turned itself off as it accelerated down and hit the ground. All right. So until we see them or don't see them, you can read or not read science fiction stories. Who knows? Okay. Let me say just one thing. So what is wrong with Newtonian mechanics now? Is Newtonian mechanics wrong? Did Newton do it wrong? And the answer is no, the theory is wrong, but it's only wrong in limits that Newton knew nothing about. He didn't know about traveling the speed of light. He didn't know about the dimensionless potential, this factor, gm over rc squared, known as the curvature. He didn't know what happened if that got to be unity, and we'll talk about that later. Ah! Did it break? Oh, good. Oh, Toshiba, that can be replaced. And he didn't know anything about this. What we know now is that these laws fail gradually. And so does quantum mechanics. It comes in and normal classical mechanics works perfectly well for anything bigger than an atom. It's only when you get to very small size or very high speed or very strongly curved space that the effects start to show up. By that we mean the theory is incomplete. But Newtonian mechanics was perfectly valid for everything it was applied to. All right, so, all right, now here's something. All of you people going out to catch black holes someday, be careful. Don't bring a black hole back to Earth, because the black hole, if you're holding it and you let it go, it'll sink to the Earth and go back and forth, and it will constantly eat the Earth up until the Earth becomes hollow, evacuated ball, and then we'll all fall in. Okay, so be careful. Besides, I think you'll have trouble finding one. Okay. All right. Good luck. And this next problem set is difficult but not impossible. Okay?